Hi, I'm Cas Maslanka. This is the part 2 video of the lecture that I gave at the Los Angeles Center for Digital Art at the Analog Sun Digital Moon Symposium. The tools on the first video will help you understand what's going on in this video, so I strongly recommend you checking it out first. But I hope you enjoyed this video as well. Thank you. Okay, we're back. So I'm going to talk a little bit about space, spatial dimensions. I'll wait for Valo. Valo's got his coffee. He's set. Tor, you all right? Good. So we're going to talk about congenital wisdom. Here this is another paradigm poem where we're using a model from Newton, his equation for gravity. So in this piece, this one, we're going to map the idea of here's the force. This is the gravitational constant. These are the masses of two bodies, and this is the distance between those two bodies. Like if we were talking about the sun and the moon, or the sun and the earth, we can calculate the gravitational force using Newton's equation here. What I'm mapping into this equation is the force of creativity. And for the mass, we're going to have the flower of Kent apple that fell at Woolsthorpe Manor. That's the mass. That'll be we got two apples in this equation. Newton's apple that fell from the tree that inspired him for this equation, and then the apple from the Garden of Eden, of the knowledge of good and evil. So we're going to map these two ideas into this equation. And of course we have the visual poetic aspects of it as well. So this equation down here, the distance between the two bodies is the distance formula, and we're going to get into that. But it's in 5 dimensions. It's in the five-dimensional space as opposed to our normal 3-dimensional space. So this is the distance between the concepts of divisiveness and concurrence. Divisiveness for the Garden of Eden, concurrence with Newton, chaos in the Garden of Eden, control with Newton, the path of sin from the Garden of Eden, the path of projectiles from Newton. This equation can be used to calculate the path of a projectile. Dissension from the Garden of Eden, ascension from Newton, attachments in the Garden of Eden, and autonomy with Newton. So let's get into it a little bit. So let's first talk about dimensions, because we're going to talk about space. So a 0 dimension would be a point. No width, no length, no height. It's just a point in space. If we want the first dimension, it's a line. We take that point and extrude it across space and we get a line. Okay. The second dimension is taking that line and going perpendicular to it in space, and we get the second dimension, which here we have a square. If we take the square and extrude it perpendicular to the other two planes, then we get the third dimension, a cube. If we take the cube and extrude it perpendicular to the other 3 dimensions, as wild as that sounds, we get a hypercube or a tesseract, which is 8 cubes in the 4th dimension. Okay? Mathematically, we can define these points. We'll talk a little bit about that. So I wanted to talk a little bit about, everybody goes, oh, the 4th dimension is time. You know, I mean, how many times have you heard that, right? That's because Einstein uses the 4th dimension for time in his equations, right? There is a 4th dimensional space, okay, where objects can exist. Now, I brought this up because here's an example of time being the second dimension, not the fourth dimension, but the second dimension. We have profits with money in one dimension, and in the first dimension's profits, and the second dimension time. These are the months and your profits. So in other words, you can use time in any dimension if you want. Depends on what the context is of what you're trying to express. Same sort of thing here. So I want to talk a little bit about the distance formula, but before we can do that, let's talk about the Pythagorean theorem. You all remember Pythagorean theorem, which says that the length of the hypotenuse is the sum of the squares of both the other two sides. So a while ago we talked about an equation. If you do something to one side of the equation, you have to do it to the other side for it to make sense. So to get to C, we need to take the square root of a square, which will give us just C, and then the other side we get the square root of a squared plus b squared. So this is the distance, the value of the length of the hypotenuse between this point and this point. This kind of shows how those squares work. I don't want to get too lost in worrying about area because we're really interested in distance. So, we talked about the first dimension, a number line. Okay? We can map things on a number line. We've done that before. We can think of terms of hot and cold on a number line. Here, you remember in class in grade school, we had the number line with 1, 2, 3, 4, 5, negative 1, 2, 3, 4, 5. And so on a number line, we can map concepts or gradients across a one-dimensional axis. In a two-dimensional Cartesian coordinate system, we have an x-axis and a y-axis, and we have our number lines. We have one number line going this direction for one dimension, another number line going for another dimension, and then we can count over 3 and up 3 and put a point here. We can count over 5 and 3 and put a point here. When you do that, that's called an ordinate pair in mathematics, in analytic geometry to be specific. So here we do with 2 and 3, go over 2 in the x, up 3 in the y, or minus 3 in the x and up 1 in the y. So an ordinate pair, an ordered pair, will tell us where these points are. You can also do it in the third dimension, but you need three ideas to do that. Okay, so here we're getting into analytic geometry, where we're just basically doing the same thing we did with the Pythagorean theorem, except we've moved it off of 0, 0. If we put this point here, we just basically get the Pythagorean theorem. We have 5 and 7, and then we can calculate and get 72 across this line. But since we've moved it, you have to add and subtract the values 9 minus 4 to get the 5, because you've moved over 4 and over 5 to give you 9. Don't want to get too wound up in that, but anyway, I just want to show you how you can map points in space. We were just mapping in the second dimension. So here's Pythagorean theorem, A, B, and C. Here's taking the Pythagorean theorem and putting it on the grid where we had those shifts in the dimensions. This is one dimension, here's another dimension. Here's the distance formula in analytic geometry where you use x and y. It's exactly the same thing, except the variables are different. So now here's the distance formula in 3 dimensions. Okay, so we have an x, a y, and a z. All we did, notice that there's just an extra term when we go to the next dimension. Here's a distance formula in the 4th dimension. So we can mathematically calculate the distance and the points in the 4th dimension. You can't see the 4th dimension, but we can mathematically describe it. So let's talk about regular geometry, and this is obviously two dimensions. Regular geometry, each of the sides are equal to each other. In the second dimension, we have a triangle, a square, pentagon, hexagon, heptagon. You can see we're just adding sides. So how many of these objects do you have in the second dimension? It's infinite. If you just keep going, infinity, you'll have a circle. Okay? Now let's go into the third dimension. So here we have regular sides. The sides are even. So we have a tetrahedron with a triangle. We can also make an icosahedron with a triangle. We can make a dodecahedron with a pentagon. An octahedron with a triangle, which is like two pyramids put together. It's kind of hard to see it here. And then a cube with squares. There's only 5 objects in the third dimension that'll do this. We had infinite in the second dimension, only 5 in the third dimension. In the fourth dimension, you've got 6 that you can do that with. In the fifth dimension, 3, sixth dimension, 3, and the seventh dimension, and on. Just 3 objects that will, in those configurations. This object here on the table is a hypercell, a hyperdodecahedron, 120 cell, where you have 120 dodecahedrons in the fourth dimension stacked around each other. Of course, we can't see it in the fourth dimension. So what is this? Well, let's talk about that. So here's a cube. If I hold up a cube, we have a 3-dimensional object, right? But also we have a shadow. We project a light on it. This is a 2-dimensional shadow of this 3-dimensional object, right? So we can see that we can take an object, mathematically we can define this as well, and project it to the next dimension down. This object exists in the fourth dimension. We can't see it in the fourth dimension, however, we can project it into the next dimension down, into the third dimension, and see it. So I just want you to get a feel that objects exist in other dimensions outside of the third dimension. Because when we start mapping poetically into other dimensions, you want to be able to feel it. So here's the dodecahedron. And this is the 120 cell, the hybrid dodecahedron. That's that same object. This is just a different vantage point of that object. Actually, we're looking right through there. So let's talk about what I call verbogeometry, basically mapping concepts in space. So here we can have a one-dimensional axis, and we put the concept of control at one end and chaos at the other. Okay? So we can have a gradient, a variation of ideas, concepts across this axis. So here in the middle we have halfway between chaos and control. Kind of like what we looked at a while ago. You got your number line, but now we have concepts and a gradient of concepts instead of a gradient of numbers. So in other words, we're mapping conceptually from this conceptual domain onto this conceptual domain to get the concrete mapped on the abstract. And here's a mathematical expression that tells us 2/3 down. So now this expression says 2/3 chaos and 1/3 control. A while ago we knew it was easy to have half and half, but you can actually create mathematical expressions to give us a feeling of chaos and control. So here's an axis where we're mapping a color between red and green. We can also map ideas, concepts onto this as well. So red is dissension, green ascension. and we get a gradient. So we can feel in between ascension and descension. More ascension, less descension. So here it is without the words red and green. And we can go perpendicular to it with blue and orange. We can add concepts, chaos and control, and get a feeling of chaos and control between these two ideas in space. Here we can map the colors, both of those two axes on top of each other, with the red and the green and the orange and the blue. And we get a variation in the second dimension. We had two one-dimensional axes, now we go into the second dimension. And we can map descension and ascension, chaos and control. So now we have different feelings of these concepts. Anywhere in this space, we get a different feeling. Here we have more ascension, more control. Here we have more dissension and chaos. So we have an axis of stability in chaos and control, and an axis of vertical movement, ascension and descension. After I put all that together, I said, wouldn't it make more sense if you would have rotated that 90 degrees? Probably would. But conceptually, it doesn't make any difference. So here we have the X, Y, and Z for 3 dimensions. You can do, here's, mapping in 2 dimensions. You can see how we can map in the 3rd dimension. Put that aside for a second. Here, let's get back to this is just kind of driving home the point. I think you guys already got it when I started talking about as you move into these areas, you get different feelings of magnitude. But here, we're multiplying. 2 times 4 is 8. 5 times 7, 35. So you can see 80, 90, 100, 144. You can feel the magnitude as you multiply these together. Or you can add them together. It's up to you how you want to view this. So here I've taken the 2-dimensional axes that we looked at a while ago. So here we have high levels of control and descension, high levels of control and ascension, high levels of chaos and ascension, high levels of chaos and descension. I'm just trying to drive home the point that you can feel concepts in space along gradients of axes in different dimensions. This is really what I'm trying to drive home. We already talked about how you can mathematically define points in multiple multiple dimensions. So here's the distance formula in the 3rd dimension. Here's the distance formula where we're using concurrence and divisiveness, chaos and control, ascension and descension as our different axes. Concurrence and divisiveness, chaos and control, ascension and descension. And here is the way it would look. Here's a point from point 1 to point 2. We're going from concurrence and divisiveness, this axis, chaos and control, and ascension and descension. And so we can calculate a point, the distance of that point through these spaces, and get a feeling of these concepts. So here is the equation in Congenital Wisdom again, because we are mapping between the ideas of 2 famous legends about 2 famous apples, Newton's apple and the apple of knowledge of good and evil. And we want to know the distance between these 2 apples conceptually, and I've mapped a 5-dimensional line through a 5-dimensional space where you can feel these different concepts in the space between these 2 apples. So there's Newton getting inspired by the apple when it fell from the tree. He saw the moon. He says, according to legend, I have a experimental physicist friend of mine who says that's just a legend. It never happened. It's not really important. The legend is really a powerful legend. The Garden of Eden may not be true as well, but it's a very powerful legend. So he sees the moon, he sees the apple fall, and he's thinking whatever's tugging on the apple is also tugging on the moon, and keeps that moon in orbit around the earth like a taut string. That's when the gravity hit him. So then he came up with the equation. The force of the gravity is equal to the gravitational constant. The gravitational constant, no one knows what that is except by experimenting. They do experiments with gravity and have calculated what this number is. So the force is this mysterious constant that when Newton thought of it, it was just mysterious. Multiplied times the product of the two individual masses of the bodies divided by the distance between them squared. So that's the equation. Here it's showing gravity actually distorts space in the space-time continuum. This is part of Einstein's general theory. So here you can kind of see a little protuberance of the Earth. Here's the sun. This page is talking about the big G versus little g. We're not going to get into little g. The big G is all we're interested in, is the gravitational constant, because we are mapping onto our equation that gravitational constant. But instead of using gravity, we're going to use negentropy. Okay? To talk about negentropy, we need to talk about entropy first. Entropy is one of the most mysterious concepts we can think about. You can imagine a place, say, halfway between here and the Andromeda galaxy, 1,000,000 light years out in the middle of nowhere. There's hardly any gravitational pull from anything out there. There's no light, because the only light would be coming from galaxies. There's no stars. There's relatively no atoms to speak of, so there's no forces of nuclear forces or anything. It's just out in the middle of nowhere. But entropy will be there. Entropy pervades everything. It's one of the most fundamental aspects and most misunderstood concepts that we can address. Technically speaking, entropy is a statistical measurement showing the level of random dispersal of energy in a system as a function of temperature. But generally what we're interested in is the difference in entropy. We're interested in the entropic states in a system, whether it's gaining entropy or it's lowering entropy. The second law of thermodynamics states that the total entropy of an isolated or closed system can never decrease over time. That means it's always increasing. And is constant if and only if all processes are reversible. Generally, everything that we deal with, in our life falls apart. So to continue here, isolated systems spontaneously evolve toward thermodynamic equilibrium, the state with maximum entropy. And you can visualize that by putting some cream in your coffee, and eventually you'll see that the cream disperses evenly throughout the coffee into a thermodynamic equilibrium. That would be the state of maximum entropy. When you first put the cream in the coffee, that would be a lower state of entropy. than when it's fully dispersed. So what entropy shows us is that in time, everything breaks down and falls apart, including our bodies. So everything falls apart. So we're constantly battling against entropy. So if we were to look at a cube of ice, and we notice it's in a lower entropy state, but in time, in a room with some heat, the entropy levels rise in the ice cube, and it melts, and things start falling apart. The ice cube is metaphorically dying, and then you get a puddle of water, and as more energy gets pushed into the water, the atoms vibrate, the energy level gets higher, and then it turns into a gas and it goes into space looking for that equilibrium that we were just talking about. So as the entropy increases, you get that full dispersal of energy in a closed system. Of course, we humans living on Earth are not in a closed system because we have the sun constantly giving us energy. So that is why we're able to live. If we had no sun, we would die. Entropy would take us out rather quickly. So on that high note, let's talk about fighting against entropy and the man who came up with the idea. Erwin Schrödinger was a Nobel Prize-winning physicist who's responsible for a lot of things. A lot of people have heard of Schrödinger's cat. That's probably the most famous thing that's been associated with him, and that's another rabbit hole that we won't get into. But what's important to us is this concept of negative entropy. Neg Trophy was introduced by Schrödinger in his 1944 popular science book, What is Life? Because life is the fight against entropy, neg trophy. So in our piece, we're using neg trophy here. So we have the two apples in space, the 5-dimensional distance between them, and the force of creativity, and the visual poetry that goes along with it. And again, the equation is between the distance between the apples, between divisiveness, the axis of divisiveness in the Garden of Eden, concurrence with Newton, chaos in the Garden of Eden, control with Newton, path of sin, path of projectiles, dissension, ascension, attachments, and autonomy, where we can feel these. So gravity bends the space-time continuum. Here's a nice apple bending the space-time continuum. Actually, my question when I saw this is in its relationship to congenital wisdom is, what is space-time metaphor in this piece, Congenital Wisdom? After I edited this video, I started slowing down and looking at the piece a little closer, and found some things that were bothering me at first. So I wanted to look at it a little bit deeper. One of the problems with doing mathematical poetry is there's not hardly anybody doing it. So there's hardly anyone out there who will criticize what I'm doing and help me, make my work better, and then I can help them make their work better. But there's very little interest in pushing it further. I have had some help from Connie Tettenborn. She's checked some of my math before and caught math errors. Those are always embarrassing, but we all need that kind of support. So anyway, when I was looking at this one, I slowed down, and one of the things that bothered me was that I'm mapping the Neg Entropy onto the gravitational constant. And one of the things that George Lakoff mentions in his theory of metaphor is that there's an invariance principle. I'll read you from the theory. Metaphorical mappings preserve the cognitive topology, that is, the image schema structure of the source domain in ways consistent with the inherent structure of the target domain. And we talked about in the first part of the lecture about mapping your source domain and your target domain, the source domain to the target domain, the source domain being concrete, the target domain being abstract. And to understand this invariance principle, it's important not to think of mappings as algorithmic processes that start with the source domain structure and wind up with the target domain structure. But it's what's important is that what the invariance principle does is it guarantees for container schemas, interiors will be mapped onto interiors, exteriors onto exteriors, boundaries onto boundaries, path schemas onto paths, path schema sources will be mapped onto sources, goals onto goals, trajectories onto trajectories, and so on. So when I'm mapping Neg Entropy, which is a measure, a variable, onto a constant, that gave me a little pause because it seems like I'm breaking the invariance principle. But there is a caveat in the other thing that I thought was interesting is it didn't really bother me. There was something there in the metaphors that still held my attention and made me think more about what was going on. So it's important. One of the caveats to the invariance principle is that the target domain overrides. So the corollary to the invariance principle is that the image schema structure inherent in the target domain cannot be violated, and that the inherent target domain structure limits the possibilities for mappings automatically. And that explains why you can give someone a kick even if they don't have it afterward. So, so the target domain on this is Neg Entropy. So the variable is what we're looking at in the metaphor, and the image schema structure, the topology of that Neg Entropy is what is holding everything together. And I think it does work. After pondering this equation and this mathematical visual poem, I came up with some things that the poem told me that I'd like to share with you. Number one, creativity, and all of these are related to each other. Number one, creativity is a fight against entropy. All creative expressions are directly related to each other through their connection to entropy. Because the big G, the gravitational constant, is universal, then creativity is universal through Neg Entropy. Number four, each creative expression, no matter which ones, are attracted to the adjacent creative expressions through their own adjacent beauty. That is, creativity is a chain reaction where every creative expression is connected through Neg Entropy. And of course, the veracity of these statements is debatable. However, I find them very interesting to ponder. And I wanted to share those with you. I hope you enjoyed the video. Thanks.